Ever wonder what it is that makes a generator generate? Well, you're about to find out in 10 minutes or less. So let's get started. What we have drawn here is a rough sketch of two magnetic poles, north and south, and then a armature winding in the center right here. Now, a couple things to note. This is connected to two slip rings. This is a common used item in AC generators to make sure that we can maintain contact with this armature to the circuit of whatever position it's in. So we have the red side, which is connected to our forward slip ring, and the blue side, which is connected to our rear slip ring, and this is connected to our battery circuit. We have a graph over here that shows the amount of voltage that's being produced over time as we rotate, and then we have two indicators right here for our flux, rotation, and current flow. Now, stepping back a little bit, the right-hand rule, if you remember that from your basic electricity, if you're like me, you're holding up your hand right now. The flux lines flow north to south, just like so. And you can see that represented with the flux line right there. If you're going to hold up your hand and do this, your pointer finger would be the flux line. So you point your finger the direction that flux is traveling. And if you stick up your thumb directly up, that is going to be the direction of rotation of the armature. So in this case, we're looking at a clockwise rotating armature. So our rotation line on this side is pointing up, and a rotation line on the opposite side is pointing down because it's going to move in a circle. Now, to figure out the direction that current is moving on that wire as it moves through our flux fields from these two poles, if you have your finger in that position, you're going to extend your middle finger 90 degrees, so pointing away from your palm, and that is going to be our current line. I didn't draw a hand because I can't. Sorry, that's just the way it is. So you can see our current flow is represented right here, as well as by the arrows that you see on our lines of the armature. Now I've divided the armature into two colors to make it a little more clear what side is doing what as it revolves and our current flow changes direction in an alternating current system. This is also kind of a dirty truth about all generating systems. If you have a DC generator, it still produces alternating current. We just have to rectify it or basically make it flow in one direction, but it still is produced as alternating current. There's a reason for that. But let's take a look first and see how this works. So right now we are showing our armature aligned in its strongest point of flux. So we are basically full register with our north and south pole. As a result, our electron flow in this direction is going to be at its highest level. And you can see that represented here. We have electron flow following the current line that we have into the circuit. We're flowing into the negative side of the battery and out through the positive. Now let's see what happens as this armature rotates. As we start to rotate, you'll notice that as we get away from that strength of magnetic field, we start to slow down the amount of current flow we have. We're going to reduce the amount of power that's being produced in the circuit, but everything's still moving in the same direction. So we're still flowing according to our correct diagram over here, and our direction hasn't changed. Again, the slip ring allows a continuous connection between the armature winding in both cases, regardless of what position it is in. So let's see what happens when we hit our next position. This is what we consider our neutral position or our neutral plane. So you can see the armature is perpendicular to the two poles, so it's halfway between, and that's going to be the point where you see we don't really have any electron flow moving. Now that's not to say that there's absolutely zero movement, but for all intents and purposes, it is slowed down considerably because we're actually at the point where we're going to start changing direction. So you can see we are perpendicular to our two poles that you see over here, and we have basically no electron flow. Now let's see what happens as we go to our next side. Now things are getting a little bit weirder because we've changed the direction of electron flow in our circuit. Now this is the part that gets kind of weird. Remember, we started with our red side of the armature aligned with the North Pole and the blue side of the armature aligned with the South Pole. Now, if we took away these colors and it was just one continuous armature winding, the current flow in that armature winding would never change. It's always going to go in this direction. And the reason being is because of how the flux lines are going to work with the rotation of that armature. But because this is connected by slip rings, remember, originally our red side connected to this forward slip ring was aligned with the North Pole. So it had electrons moving towards the top of the screen. As a result, our flow in the circuit was going to follow that pattern, right? And that same clockwise motion around the circuit from positive to negative. However, because our red side is now aligning to the south pole, but it's still connected to that same slip ring, we've flopped directions. So now our flux, or our electron flow due to the flux, is coming through that slip ring, and we've reversed the direction that the circuit flows. Back that up a little bit. Before we hit that neutral position, you can see we were flowing clockwise through. Once we go past our neutral position, it's flopped. Now we're flowing counterclockwise in that circuit. And as we come to our full register position again, now our red side is fully aligned with the south pole and the blue side is fully aligned with the north pole, and we've established our highest current flow in the opposite direction. That's how that works. Now, this is an AC generator. It's going to generate current flow in both directions, and we can use that pretty effectively. Nice thing about AC is we can tend to work in much higher voltages, which means we need smaller currents to be able to transmit energy over long distances, which means we need thinner wires and we save a lot of weight. The other thing that's useful about AC is we can step the voltage up and down pretty easily using transformers. So that really makes it pretty advantageous, but it also makes it kind of tough if we're working on things that require direct current, like charging a battery, for instance. Now, something that's interesting about this is the power output of our generating system, no matter what it is going to come down to three things, basically. We have the strength of the magnetic field being produced by our poles. So a stronger magnetic field is going to result in more electron movement as our armature wire breaks those flux lines. If we have additional wires, then that can increase the amount of power produced. Or if we speed up the rotation of the armature, the faster the armature goes, the more voltage and current we're going to produce. Now, let's see how we can change this to go from an alternating current system to a generator that can produce direct current. So what you notice is this is effectively the same drawing that I just had, but there's one crucial change that I've made. I have added a split ring here instead of two slip rings. Now all this split ring is we have one conductive side of the ring and a second conductive side of the ring, but now there's a mica insulator that separates the two halves from each other. So these are not going to be able to branch. They're electrically separate, and we have carbon brushes that ride on either side of this split ring to transmit energy from the ring over to the circuit. So let's see how this works. Everything else is going to be the same. Our rotation, the direction the current flows, it's all going to be the same. So we start off at our highest amount of current flow. Up here on the positive side, we're flowing clockwise through the circuit. Everything's fine. As we start to rotate, we see the exact same thing happening as before. We are starting to diminish the amount of potential here because we're starting to get further away from our full register position with our magnetic poles. And again, when we hit our neutral register right here, we are going to be at basically nil electron movement. Again, not to say it's completely still, but it's going to be pretty close. We don't have anything appreciable from a electrical capacity standpoint. Now watch for something crazy to happen. As we go past our full register, so we flip our blue side for the red side, notice what happens. First off, we don't go into the negative register. The drawing is like this for a reason, but we don't do it. Why? Because our electrons, they haven't flipped. The currents remain the same. So instead, we now found ourselves in a situation where, because of this split ring, before we had two slip rings and they stayed connected to the same side. However, as we transition over from this neutral position onto the other side, this red side of the armature is now connected to the right side of this split ring, and the blue side is connected to the left side of that split ring. As a result, the current flow in this armature remains the same. Even though the sides have swapped, we have gone to different connectors. So they're electrically insulated from each other, and we get the same direction of current flow. Seems crazy, but it's just how it works. Over here, red is connected on the left side, and on that side, when it's aligned towards the right pole, it's going to, or the North Pole, it's going to be moving towards the top of the screen there. However, as we flip over, it crosses over that insulating barrier, and now it's traveling the opposite direction, but it's no longer connected to this side, so it doesn't force the electron flow to go in the other direction. Now it flows in the original direction that it had. And so that graph that we're talking about with our voltage over time, we started off at our highest potential, and we came down to our neutral position. Now we've come to a spot where we've bounced back up instead of going down in the opposite direction. As we see, we end up over here at our full register position. And again, we can ignore this point because we didn't reverse our current flow. Instead, what's happened is we've bounced back up to another peak, and we'll have another flow. Now you'll see, instead of the sine wave that you see with alternating current, what we have now is this little bouncy peak that goes across the top because it's only flowing in one direction exclusively because of the split ring. The split ring is effectively what we call a commutator. That's what we use in DC generators to rectify this alternating current into usable direct current. Now to compare the two, right, we have this little bouncy pattern we see of current flow on our DC generator side. It's all going one direction, so that's fine. Well, you'll notice that we have gaps in between, and we have points where we start off with a high potential, and then we drop down to basically zero, and then it has to build back up again. That would not work particularly well if we have a system that requires a constant amount of voltage to be able to power things like lights. If we had that operating with a light system, you would see the lights pulsate or flash. And that's all we want. We want consistent energy. So one of the things that we can do is we can add more poles, and we can add more armature windings in different positions to be able to fill those gaps. Now this would just be a situation where we have two windings or a couple sets of poles, but you can see that we can fill that valley with another armature passing through another pole. If we multiply that a couple different times, then we can see a pretty consistent amount of power being produced throughout the entire phase of this generator's operation. Now, this little bounce pattern that we see at the top, this is referred to as ripple current. So that little bit of cycling that we get, it's just going to be a barely measurable drop from maximum voltage to slightly below. It's going to oscillate at a regular frequency, and that's our ripple current. Now, on the other hand, with a DC alternator, the alternator is producing AC current, but instead of using a commutator to accomplish that, we use a rectifier, basically diodes, that prevent electron flow in the opposite direction. So it can only be pushed out in one direction. Now, what you see depicted here is pretty similar to what we talked about before. These red lines depict our rectifier, so preventing electron flow in the opposite direction. Now, this is kind of a problem, though, because we just have a single phase of alternating current being produced. You can see we start off on the positive side, but then we have this entire dead period when it would be flowing the opposite direction, but we don't get any power. And then we come back up to our peak power again, and then we drop down. Since we aren't using everything below the middle line or the neutral line of this graph, we can use additional phases. Additional phases in AC current generation do kind of the same thing as additional windings and poles in our DC generator. It basically fills the gaps. So we have another phase which is operating to produce current. It's going to have its own sine wave that's slightly out of phase with the first. Because it's slightly out of phase, we have current flow in the same direction. Now this works with a